You will now learn to generate counts, which you can then use as features into your logistic regression classifier. Specifically, given a word, you want to keep track of the number of times that word shows up in the positive class. And given another word, you want to keep track of the number of times that word showed up in the negative class. Using both those counts, you can then extract features and use those features into your logistic regression classifier. So let's take a look at how you can do that.
It is helpful to first imagine how these two classes would look. Here, for instance, you could have a corpus consisting of 4 tweets, and associated with that corpus, you would have a set of unique words, your vocabulary. In this example, your vocabulary would have 8 unique words. For this particular example of sentiment analysis, you have 2 classes. One class associated with positive sentiment and the other with negative sentiment. So taking your corpus, you would have a set of 2 tweets that belong to the positive class and a set of 2 tweets that belong to the negative class. Let's take the set of positive tweets. Now take a look at your vocabulary. To get the positive frequency of any word in your vocabulary, you'll have to count the times that it appears in the positive tweets. For instance, the word happy appears 1 time in the first positive tweet and another time in the second positive tweet. So its positive frequency is 2. The complete table looks like this. Feel free to take a pause and check any of its entries. The same logic applies for getting the negative frequency. However, for the sake of clarity, look at an example. The word am appears 2 times in the first tweet and another time in the second one. So its negative frequency is 3. Take a look at the entire table of negative frequencies and feel free to check its values. So this is the entire table with the positive and negative frequencies for your corpus. In practice, when coding, this table is a dictionary mapping from a word class, pair, to its frequency. So it maps the word and its corresponding class to the frequency or the number of times that word showed up in the class.
You now know how to create a frequency dictionary, which maps a word and the class to the number of times that word showed up in the corresponding class. In the next video, you're going to use your frequency dictionary to represent a tweet. You will now get an overview of logistic regression. Previously, you learned to extract features, and now you will use those extracted features to predict whether a tweet has a positive sentiment or a negative sentiment. Logistic regression makes use of a sigmoid function, which outputs a probability between 0 and 1. Let's take a look at the overview of logistic regression.
Just a quick recap. In supervised machine learning, you have input features and a set of labels. To make predictions based on your data, you use a function with some parameters to map your features to output labels. To get an optimum mapping from your features to labels, you minimize a cost function which works by comparing how closely your outputs y hat is to the true labels y from your data. After which the parameters are updated and you repeat the process until your cost is minimized. For logistic regression, this function, f, is equal to the sigmoid function. The function used to classify in logistic regression, h, is the sigmoid function. And it depends on the parameters theta and in the features vector x superscript I, where I is used to denote the ith observation or data point. In the context of tweets, just the ith tweet. Visually, the sigmoid function has this form, and it approaches 0 as the dot product of theta transpose x over here approaches minus infinity, and 1 as it approaches infinity. For classification, a threshold is needed. Usually, it is set to be 0.5, and this value corresponds to a dot product between theta transpose and x equal to 0. So whenever the dot product is greater or equal than 0, the prediction is positive. And whenever the dot product is less than 0, the prediction is negative. So let's look at an example in the now familiar context of tweets and sentiment analysis. Look at the following tweet. After pre-processing, you should end up with a list like this. Note that handles are deleted, everything is in lowercase, and the word tuning is reduced to its stem, ton. Then, you would be able to extract features given a frequencies dictionary and arrive at a vector similar to the following, with a bias unit over here and two features that are the sum of positive and negative frequencies of all the words in your process tweet. Now, assuming that you already have an optimum set of parameters, theta, you would be able to get the value of the sigmoid function, in this case equal to 4.92, and finally predict a positive sentiment.
Now that you know the notation for logistic regression, you can use it to train a weight vector theta. In the next video, you will learn about the mechanics behind training such a logistic regression classifier. Now that you have your theta, you will use this theta to predict on new data points. For example, given a new tweet, you will use this theta to say whether this tweet is positive or negative. In doing so, you want to analyze whether your model generalizes well or not. In this video, we will show you whether your model generalizes well or not, and specifically, we'll show you how to compute the accuracy of your model. Let's take a look at how you can do this.
For this, you will need xval and yval, data that was set aside during trainings, also known as the validation set, and theta, the set of optimum parameters that you got from training on your data. First, you will compute the sigmoid function for xval with parameters theta. Then, you will evaluate if each value of h of theta is greater than or equal to a threshold value, often set to 0.5. For example, if your hx theta is equal to the following vector, 0.3, 0.8, 0.5, etc., up to the number of examples from your validation set, you're going to assert if each of its components is greater than or equal to 0.5. So is 0.3 greater than or equal to 0.5? No. So our first prediction is equal to 0. Is 0.8 greater than or equal to 0.5? Yes. So our prediction for the second example is 1. Is 0.5 greater than or equal to 0.5? Yes. So our third prediction is equal to 1, and so on. At the end, you'll have a vector populated with zeros and ones indicating predicted negative and positive examples, respectively. After building the predictions vector, you can compute the accuracy of your model over the validation set. To do so, you will compare the predictions you have made with the true value for each observation from your validation data. If the values are equal and your prediction is correct, you'll get a value of 1, and 0 otherwise. For instance, if your prediction was correct, like in this case where your prediction and your label are both equal to 0, your vector will have a value equal to 1 in the first position. Conversely, if your second prediction wasn't correct, because your prediction and label disagree, your vector will have a value of 0 in the second position, and so on and so forth. After you have compared the values of every prediction with the true labels of your validation set, you can get the total times that your predictions were correct by summing up the vector of the comparisons. Finally, you'll divide that number over the total number m of observations from your validation set. This metric gives an estimate of the times that your logistic regression will correctly work on unseen data. So if your accuracy is equal to 0.5, it means that 50% of the time your model is expected to work well. For instance, if your yval and prediction vectors for 5 observations look like this, you'll compare each of their values and determine whether they match or not. After that, you'll have the following vector with a single 0 in the third position where the prediction and the label disagree. Next, you have to sum the number of times that your predictions were right and divide that number by the total number of observations in your validation set. For example, you get an accuracy equal to 80%.
Congratulations on finishing the first week of this specialization. You learned many concepts this week. The first thing you learned is you learned how to pre-process a text. You learned how to extract features from that text. You learned how to use those extracted features and train a model using those. Then you learned how to test your model. In this week's programming exercise, you're going to get a chance to implement all these concepts that we spoke about. Feel free to go ahead and do the programming exercise. There's also an optional video at the end of this week which covers the intuition behind the cost function for logistic regression. If you don't want to watch that video, feel free to go to next week, where you will learn about a new classification algorithm known as naive Bayes.
Welcome to this interview series. To kick it off, I'm delighted to have with us today Chris Manning. Chris is, I believe, the most highly cited NLP researcher in the world. He is a professor of computer science and linguistics at Stanford University. He's also the director of the Stanford AI Lab, which is a role that I had previously held as well. Chris is well known globally as a leader in applying deep learning to natural language processing and has done well-known research on tree recursive neural networks, sentiment analysis, neural network dependency parsing, the glove algorithm, and a lot more. He's taught at Carnegie Mellon, the University of Sydney, and at Stanford University. Welcome, Chris.
Thank you, Andrew. It's great to have a chance to chat.
Even though you and I, Chris, have had the opportunity to work together on many occasions, one thing I've actually never asked you before is, how did you get started working in AI? I know that one of the unusual aspects of your background is that you majored in linguistics and then wound up being a computer science professor doing NLP. But tell us about your arc getting started in AI.
Sure. So my background in some sense isn't as a AI person. That's not really where I began. So as an undergrad, I have a major in computer science and math, but I also got very interested in linguistics and did a major and honors in linguistics. So coming off of that, to a fair extent, my starting off point was a much more cognitive science viewpoint of human language seemed fascinating. These teeny little human beings somehow managed to learn it at a time where, in general, their cognitive abilities don't seem that great. And how could human language learning take place? And so in linguistics, by far the dominant belief in sort of the second half of the 20th century was the thinking of Noam Chomsky, that Noam Chomsky was just the eminent person in linguistics, in the same way that I guess for the first half of the 20th century, maybe R.A. Fisher was the dominant person in statistics. And Chomsky has had this very strong position that humans cannot possibly just be learning languages from data alone, and that there must be innate machinery in people's brains that allow them to learn languages. That's a big topic. Even back then, this seemed to me kind of just unbelievable, given this evolutionary, extremely recent development of human language. So I was interested in the idea of how could you go about learning languages. And that led me to start to look at machine learning, starting off first at the end of my undergrad, which was the late 1980s. And these days, machine learning is such a big and dominant field. It's so big and dominant that the terms artificial intelligence and machine learning are kind of 2/3 the same thing, because the vast majority of what you see in AI is machine learning. But at that time, it just wasn't like that at all, right? That machine learning was this sort of very scruffy on the side offshoot of AI that almost no one worked in. So, there were sort of these series of 2 or 3 books by edited by Jaime Carbonell and Tom Mitchell from CMU, who had started to sort of put together some papers on machine learning. And the early decision tree algorithms, this was while I was still in Australia, so the early decision tree algorithms in AI, the ID3 algorithm that had seen decision tree learning, but machine learning barely existed. But I was sort of interested in these ideas of how you could go about getting computers to learn, and that was sort of the entree that led me down the path that's turned me into an AI researcher.
And it was a big deal, right? It was maybe not intuitive at the time that you should use data to learn from language rather than code out by hand a CFG grammar or something to truly understand the language, which is what people were trying to do back then.
Right. Yeah. So the dominant way in which people did natural language processing was by humans. I mean, of course, that wasn't only a fact about NLP. That kind of corresponded to the dominant thinking of AI at that time as well, right? This was the era of knowledge-based systems where what was seen as what we needed was to get subject matter experts for which knowledge engineers would encode their knowledge in knowledge representation systems, and that all of this hand engineering would lead us to intelligence.
So even back then, you're an early believer in machine learning for NLP.
Absolutely. Right at the moment, transformer-based architectures have really become the dominant thing in neural networks, and we're sort of going out of order here, so maybe we should get back to them later. But I mean, the interesting thing about transformer architectures is that they're built around an idea of attention, and you can think of attention as giving you sort of a soft tree structure where you can sort of point it from one word to another, and that allows you to build a tree structure. So we've done some really interesting work, especially my PhD student, John Hewitt, looking at what do transformer models learn when trained on billions of words of a human language? And you can actually show that these models learn all kinds of things about the structure of a language. One of the things they learn is that they learn some of these co-reference facts, so that they'll learn that she refers back to Susan, and that it is referring to the bottle in sentences. But they also actually do learn this hierarchical context-free grammar structure of languages just from a pile of sequence of words in a text alone, which is actually a really neat result.
Because language can be reasonably described as this nested context-free grammar-like tree-like structure. A neural network or sufficiently large neural network or transformer network discovers aspects of that just from the data.
Yeah.
And in fact, in the lead up to the modern views on transformers, your group at Stanford did some of the very influential early work. So I know that for a long time in the pre-deep learning days, you did a lot of work on statistical machine translation. And then as deep learning started to make inroads into NLP, you and your PhD student, Thang Long, actually published one of the earliest papers on neural machine translation, and helped lay the foundation, with the bilinear attention matrix, but helped lay some of the foundations of the modern transformer model. Do you want to just tell us a bit about that?
Sure. Yeah. So really, before starting work in neural networks again, I actually did a teeny bit of neural network work back in the 90s and the days when David Mulhart was at Stanford. But it, really, I barely got into that. And so in the 2000s decades, certainly everything that I was doing was using probabilistic modeling techniques, putting probabilities over symbolic structures to describe human languages, which was by far the dominant approach in that decade. And one part of that work that I worked on for about a decade was building machine translation models. The dominant models were referred to as statistical phrase-based machine translation in those days. And a lot of techniques were worked out pretty well in that time. So there's a fairly well worked out architecture where you have these factorized machine translation models, where part of it was that you had phrase tables, which gave you probabilities of translating a phrase in one language to a phrase in another language. So that they did the local parts of translation. And then you were combining it with what's called in natural language processing a language model. So language model is kind of a term of art that's very dominant in natural language processing. So a language model means something that gives you probability distributions over sequences of words in a language. And that's just been a really dominant, powerful idea in NLP because it lets you just tell whenever you want to sort of have words next to words, what other words are likely or unlikely. So this basic idea of a language model has used context-sensitive spelling correction. So when you have something like, Google correcting your spelling in context beautifully, there's a language model. Speech recognition systems use language models, and these machine translation systems also use language models. So we had architectures and they worked reasonably well. So when Google first came out with machine learning-based learn from data machine translation systems, they were using these statistical phrase-based machine translation systems. If I back up just for a teeny little bit of story, when Google first launched machine translation, they licensed a very traditional, old, rule-based machine translation system. And that sort of was a system that was originally developed by this company, Systran, whose roots go back really to the 1950s from the earliest explorations of machine translation. But they had that for a couple of years, and then seeing the sort of all the advances that are being made in probabilistic models for machine translation, they vectored over to that, and then things got much better. And
and I remember Franz Ox was the am I saying his name?
Yeah, Franz Ox. Yeah.
And remember, Franz Ox was really a real thought leader in helping Google scale to training the traditional models on tons more data, and just dramatically improve the performance of Google Translate.
Yeah, so absolutely. So at that point, Franz Ock was one of maybe even the leading person doing statistical phrase-based MT models, and he went to Google and led a team that then Google had the sort of leading large-scale implementation of statistical phrase-based MT models. And, they actually worked pretty reasonably. They already achieved the goal that you could just sort of feed any web page and dozens of languages in and get something that was 2/3 comprehensible. You could work out basically what it was saying about what topic. And sort of that was reasonable, but, that was sort of great for 2007 to 2010, but sort of 2010 to 2014, which was sort of the same period where Andrew and me were doing those tree recursive neural networks we were just talking about. In that period, statistical phrase-based machine translation sort of stalled. There weren't really very good ideas for making further progress, and a little bit of progress was being made by just throwing more data in. More data helps. That's still true in modern machine learning, but the models didn't have enough capacity for it to help a lot. An idea that people were working on a huge amount, including me in those years, was saying, well, surely the solution is to make more use of grammatical structure of human languages in our machine translation systems. So really the dominant research area was trying to do syntax-based machine translation systems. But that seemed a good idea, but, that barely ever worked, right? That basically the result was that for some language pairs, that it didn't work at all. It just wasn't better than the statistical phrase-based machine translation systems. Whereas for some other language pairs that had sort of more different grammatical structures, actually English, Chinese, machine translation was a good example. It definitely did help a bit. You could show some real gains, but
the solution ironically turned out to be to pay less attention to the syntax and more attention to the data.
Correct. Yeah. So that work kind of got blown out of the water when people started exploring using neural methods for machine translation. And this was really, I was going to say it was the first big success of neural methods in NLP. Whether that's true or not depends on whether you count speech as part of NLP or not, because really speech recognition was the first huge success of neural network methods applied to human language problems. But for text-based work, really the first thing that was just a sort of knock you out was building neural machine translation systems. And it was a very successful domain because it's a domain where there's sort of lots of data available of here's a lot of text in a pair of languages that you could start to train big neural network models. And it was first done by Ilya Sutskever and a couple of colleagues at Google. And for modeling a sequence of anything, like a sequence of words or a sequence of DNA, that the dominant model is recurrent neural networks, which are just models that work on simply sequences and sort of remember what they've seen before in a limited way. It's kind of like it's the continuous neural version of a hidden Markov model. And so essentially what they showed is if you made no use of the structure of human languages at all, so this is kind of undermining all that work on syntax-based models, was that if you just build very large recurrent neural networks that were then deep, right? Until that point, most of the neural network modeling in NLP was that, if we had 2 layers, we called it deep. And if we had 3 layers or 4 layers, we were really pushing it, where they were immediately sort of pushing it out to 8-layer deep recurrent neural networks. And this is where you start getting into systems issues of needing to sort of run it on a machine with 8 GPUs to get, which is a trend that's continued and we can maybe talk more about. So they showed that a much larger neural network just training big sequence models, so 2 sequence models. One is an encoder that encodes the source language, then another run as a generator that generates a sequence of words in the target language, could already give you a pretty good machine translation system. Not quite as good as the state of the art at that point, but it was close enough to the state of the art to seem tantalizing, since all they were doing was plugging 2 neural networks together, the kind of thing that, if you're not counting the library code for having recurrent neural net units, in particular LSTMs, long short-term memory units, were sort of very influential in allowing this work to work. You sort of only needed your 500 lines of Python code around the neural network library, and you could have an almost state-of-the-art machine translation system. That seemed just super intriguing. But there also seems something crude and missing there. And so then very quickly after that, Kyung-Hyun Cho, who was working with Yoshua Bengio at Montreal, well, actually, not only Kyung-Hyun Cho, also Dima Badanao, I should mention, as the first author on the paper, who was then a younger student in Montreal. So it was really actually, I think, Dima who developed the idea of you could build an attention-based model. And the idea of an attention-based model is that at any point in the sequence, you could calculate out a connection to other words in perhaps the same, perhaps a different sequence, and then using that attention, you could kind of calculate a new vector to influence what happens next. So in particular, in this machine translation context, you'll have started your translation, and your translation is starting to say the pilot, and then you'd calculate attention back into the source sentence in the other language and work out essentially what words in the source you want to be translating next based on what you've translated so far. And so rather than having to remember the entire of the source sentence in your current neural network state, you could do what a human translator actually does and dynamically look back at the source sentence and work out what to translate next. And so this idea of attention has just been transformative. It's also being used and increasingly being used also in vision systems for knowledge graphs and other areas of work on neural networks. So they did that.
Oh, and then how did and then shortly after the Cho and Dima paper, you and Thang wrote a paper on bilinear attention. How did that come about?
Right. So in earlier work, sort of really starting with another student, Danchi Chen, that we'd looked at this idea of neural tensor networks, where what we'd wanted to do is sort of be able to combine together vectors and have them influence each other to produce another vector. And we'd done that by sort of putting tensor, which is the multidimensional generalization of matrices in between them. So, that idea was sort of going on in other pieces of work in my group at the time. But, here we just wanted to get an attention score. And so in Dima and Cho's work, what they had done is said, okay, we want an attention score between these two vectors. Let's feed them through a little neural net, a little multi-layer perceptron, and calculate an attention score. Whereas it seemed to me that, well, wait, no, I could just do this simpler thing of bilinear attention, where here are these two vectors. If I put a matrix between them and I multiply vector times matrix by vector, I just get a number out. And so that is bilinear attention, or now sometimes referred to as multiplicative attention. And it's a simpler and more directly interpretable idea of attention, because in some sense, the simplest idea of attention is to say, well, you have two vectors, just dot product them together, you get a score for similarity. But that's too rigid, because you sort of want to say, well, maybe I only want to pay attention to parts of the vector, and maybe I want to know if the top part of one vector is similar to the bottom part of the other vector. And so by sticking a matrix into the middle, you can then sort of modulate the similarity calculation. That's a natural measure of similarity and very easily learnable by neural networks. And in some sense, it's a generalized... There's sort of how ideas developed and spread is always sort of complex. There are a lot of ideas in the air at any one time. But in some sense, what's become dominant in the modern work with transformer-based models essentially does build off that notion, but adding in an extra idea on top of it.
It's a similar idea where instead of having a giant matrix in the middle, which requires a lot of parameters, if you have a low rank approximation to that matrix in the middle to what you were using, then that gets very close to the modern transformer model.
Right, exactly. So in our initial work, we just had a full rank matrix in the middle, but the flaw of that is you have a full rank matrix with a lot of parameters, and the obvious way to have less parameters is to say, well, no, I can regard that matrix as being the product of two low rank matrices. And then once you have that idea, rather than sort of multiplying them together, you can say, well, I can sort of apply those two low rank matrices to the vectors on each side, which is more efficient computationally, as something to do. And that's exactly what modern transformer models do, that you take your two vectors, you multiply each by a low rank matrix, and then you take the dot product between those, which is exactly equivalent to saying I form the matrix by multiplying two low rank matrices, and then I do my vector matrix vector product, but done more efficiently.
In fact, not to jump around too much, I feel like this is not the first time in your career that you really advanced the field by making observations about matrix multiplications. If I look at the work that your team did on Glove, the word embeddings, I feel like the heart of that idea was also simplifying what was a relatively complex, set of neural network-like stuff into just a set of matrix multiplications. Do you want to talk about that? I still find Glove to this day a very elegant paper because it really simplified what was previously a very complicated, set of ideas for learning word embeddings into simpler, take the inner product between the word embeddings kind of formulation.
Thank you. Yeah, I do think the Glove paper, in some sense, it's one of its main contributions was, giving better understanding. I mean, it's not that it worked better than the other methods have been recently being developed, but it was interesting. Let's try and think about what's going on here and how these methods relate to other things that have been explored. And so, so our general topic here is word vectors, of coming up with a real vector representation that gives you the meaning of words, and which now in your NLP deep learning course is essentially often the first idea you really see, because it's a very useful notion and a fairly simple one. And this had been done quite successfully by a couple of pieces of work in the few years around 2010 to 2013, but it had been done in very mechanistic neural net ways of, here's the architecture and the algorithm, run this, and run it in those days often for weeks, because we didn't yet have very fast parallel computers, and out the end will pop great word vectors. And we were interested, so this was work with postdoc Jeffrey Pennington, we were interested in actually trying to understand better what was happening in terms of the math of these models. And so, something that we were intrigued by was, actually there was an older tradition, the LSA, or latent semantic analysis tradition, of having vector representations of word meaning, which exploited classical linear algebra. So the latent semantic analysis models in linear algebra terms were neither more or less than the singular value decomposition, or using the singular value decomposition on word count, co-occurrence count matrices, and then reducing rank via getting rid of small singular values.
That's fascinating. And one trend that overlays all of this work that you've observed and participated in for the last many, many years is the scaling of NLP models. It seems like the state-of-the-art NLP models are getting larger and larger, like GPT-3, but really many models in the sequence. For how long do you think this will continue? And do you think someday, if ever, we'll go back to building smaller models?
In 2018, BERT came out, and it showed that you could do fantastically well on a bunch of tasks, including question answering, natural language inference, text classification, named entity recognition, parsing, making use of this pre-trained large language model where you are training a large transformer just on a few billion words of text to predict gapped words and sentences, but just doing that simple task gave you these really good language representations, which then could just be used in a very simple manner with something like a softmax classifier to provide great solutions for downstream NLP tasks. So, that was an amazing success, right? And the idea of representation learning that many of us have been talking about for a decade, we're saying that, neural networks, it's about representation learning these useful intermediate representations. And this was really showing that this was really working for building representations of language that could then be very easily applied to higher natural language understanding downstream tasks. But BERT already used a huge amount of data and compute. So it was trained on billions of words of language, and it was trained on, large numbers of computers for quite a long time. But since BERT, there's been a lot of further progress, but it's essentially just come from scaling up the compute more and more and more. I mean, as always, I'm leaving a few things out. There've also been a couple of new ideas. There's been ideas like doing relative attention, which has improved things. But to a first approximation, what's really been driving the gains is just by throwing more and more compute at the problem, running even bigger models on even more data. So Andrew often use the slogan, AI is the new electricity. In some of the talks I've been given recently discussing this trend of bigger and bigger models, I've been turning it around and saying that electricity is the new AI. Because if you look at what's been happening, people are now training models that are not just 10 times or 100 times bigger than the BERT model. They're training models that are 10,000, 100,000 times bigger than the BERT model, and the computational and energy demands to train those models is going up accordingly. So, that's certainly pushed progress. I think that trend can't possibly continue much further. I mean, part of it is just we're running out of text and we're running out of computers to train ever bigger models on.
Although going from BERT to GPT-3, if I remember, there was massive scaling of compute and modest scaling of data. So maybe we have enough text data. We just need, another 100 or 1,000 or 10,000 times faster computers. I don't know.
So you're right that the scaling of compute was vastly bigger than the scaling of data. But nevertheless, the amount of data that's now being used is actually, quite substantial. I mean, there's certainly more data, but, they actually are using a sort of a substantial quantity of quality data. But yeah, I buy the point that to the extent that clever systems people can give us 3 orders of magnitude more power from our GPUs, even without more text data, these models are going to be better and probably will be made better in the coming years. But, I don't ultimately believe that's the path to artificial intelligence or the interesting path at this point for further improving natural language processing. I mean, there's no doubt that...
So let me ask maybe a slightly controversial question. Several weeks ago, one of our mutual friends made a comment, about this direction that said, "Oh, maybe the scale is a path toward AGI." Right? You're in that conversation where one of our mutual friends made that comment. What are your thoughts on that?
So I think there's a place that idea is coming from. So the really cool thing about the GPT-3 model that was recently released by OpenAI was the discovery that then really motivated their subsequent work, that with these really humongous language models, that they can actually achieve a generality where they can be used for all kinds of tasks without actually having to train them to do any task. So, conventionally, if we wanted to do different tasks with a neural network, we'd just take data for that task and train a model for that task. With these large pre-trained language models like BERT, we sort of got to a halfway house where we had a baseline, very good language representations have been pre-trained, but still we then just fine-tune it for every different task. So we fine-tuned it as a question answering model, and when we'd start again and fine-tune it for something else like summarization or something like that. And what they discovered with GPT-3 is that actually you didn't need to do that anymore, that instead you could just hint to the model what you'd like it to do by giving it a couple of examples. So you'd say, okay, I'm interested in, translation. So if here's a sentence, what I'd like you to produce is this sentence, which is a translation of it into Spanish. And if you gave it a couple of examples of what you wanted it to do, the model would get the idea, and then you could give it more sentences and it would translate it. But it didn't only do translation. You could give it some questions and tell it you wanted answers, and it would give answers to other questions. And the sort of mind-blowing thing about GPT-3 is, to a first approximation, you can give it all kinds of tasks, even, sort of weird ones that you wouldn't expect it to really know why it knows it, and it'll just do them, right? So sometimes the kind of things that linguists are interested in is sort of weird sentence manipulations. If I give you a sentence, can you turn it into a question sentence, or can you turn it into a relative clause that modifies the person? And any of those things, you can just give it as a little task to GPT-3 and it will do it. So that's the sense in which it actually offered a vision of general intelligence, rather than what's been the mainstay of AI over the last decade, which was these very narrow AIs where you just trained a system for one particular thing. Here's a movie recommender, here's an object recognizer in images, here's a natural language question answerer. And so it's intriguing because of its general intelligence, but I don't actually believe it represents something that's a path to the goals of artificial general intelligence, which is to have the kind of flexible cognitive agent like human beings, because it is just this humongous pre-trained model trained on an amount of data that is just massively more than a little human being sees before they're competent at human language. And it's not, to have something that's like a human being, you have to have something that can flexibly learn different tasks as it's exposed to them. The big GPT-3 model, it's no longer learning at all. It's been exposed to so much data at training time that it can do all sorts of different tasks by sort of effectively pattern matching to something it saw somewhere along the line. That's actually an area that there's also starting to be a lot of work on right at the moment in deep learning, is the idea of meta-learning, as to how do you build systems that are good at learning how to learn new tasks. And I think that's actually closer to the kind of intelligence we have to be seeking if we're aiming at having artificial general intelligence.
And then, Chris, in your career, you've mentored tons of very successful, undergrad students, master's students, PhD students, and today there are many people applying to be a student in your lab. So I'm curious, in your view, what makes a good researcher, in your lab at Stanford? What characteristics do you like to see in people applying to be a member of your lab?
So there are definitely people that come from different backgrounds. I certainly do actually like some of my students to know something about and really be interested in human languages and their structure. So, I certainly like to have some people that have backgrounds in human languages and linguistics, but that's certainly not all of them. I've had other people who are AI, machine learning, or other quantitative students who have no background at all, apart from, like all human beings, they're native speakers of some language or another. I think, the dominant thing is that you have to have creativity and a scientific thinking right? I mean, there are lots of people around who can read papers and do whatever's in them. The secret of being successful is that you can think a bit differently and say, wait a minute, these people are doing things like this. In fact, almost everyone's doing things like this. But maybe there's another way it could be approached that is better. And really, I think that's sort of core sort of scientific training of trying to sort of aim to break things in the sense of find why these ideas aren't actually a great way to do things and to think of different approaches which might work better.
And how does a student become creative?
That's a good question. Yeah, I believe that you can make progress on this, and I think it's a matter of taking a mindset of being critical when you read things and starting to explore around and do different things. So rather than sort of just reading papers and thinking, oh, this is a good way to do things, I think you really want to be concentrating on being awake as you read and trying to think, well, what are they assuming? Why are they doing it this way rather than some other way? And well, a lot of times your experiments will fail, but I think when they fail, you're already learning more than if you're simply implementing the algorithm that's in the paper, because you sort of don't really learn very much by doing that. And, occasionally you might see something that half works, and then that might give you an idea of, maybe there's something here, and if I sort of modified it or pushed it and had a sort of a second vector of what people do now, then it might work interestingly better. And I think the practice of sort of exploring out and thinking in those directions is the way that you sort of build these skills of coming up with something new.
See, cool. Yeah. And I find a lot of the most creative people read incredibly widely and wind up making strange connections that someone else wouldn't have made between linguistics and computer science, or between some other weird thing and deep learning. So
yeah, I think that's also a really good strategy.
hey, so thanks, Chris. This has been great. And before we wrap up, I think a lot of the learners watching this video are looking to build a career in AI, looking to build a career in NLP. Do you have any final words of advice to someone watching this looking to advance their career in AI?
Sure. So, I mean, it's a great time for you to do this, right? That there's just huge opportunities all over industry and also in academia for people with skills in AI, machine learning, natural language processing. You'll be greatly in demand. So this is a great thing to do. But I think nevertheless, you want to think thoughtfully about how to develop your career. And this is maybe connected with what, Andrew, you were just saying about reading widely, because the reality is that the world and the skills that are useful develop quickly, right? So that we've talked about earlier in this hour that, really when I started off, I was being taught about rule-based NLP, and then there started to be machine learning models and probabilistic models. There are other things that went by in the meantime, like support vector machines and large margin models. And then there was the return of neural networks to dominance. But neural networks were actually an idea that had been around since the 1950s, right? So that at the moment, deep learning and neural networks seems so dominant, it seems like, nothing else can possibly be relevant to know. The only thing I should learn is how to be state-of-the-art in building neural network models. But, that's not how the world has been in the past. Around 2008, that's what we thought of probabilistic AI models. They were obviously right and dominant, and they were the thing to know. But, really, progress is made by sort of taking old ideas and rediscovering them and putting them together with some stuff that's been learned in the meantime, and sort of further raising the bar on where we can get to. So it's just sure to be the case that lots of different ideas are going to be useful in various ways in the future. And so to be successful long term, it both helps to have a richness of background. It definitely helps to, have some breadth of areas of computer science, areas of math, statistics, linguistics, different ideas. But you also have to accept that this is an area where you have to adapt and move on to new ideas. I mean, I think one of the ways in which I've been very successful is not by, inventing a whole new field single-handedly, but being able to see where promising ideas were emerging and moving, starting to think about those and moving to do work in them fairly quickly. And so that kind of keeping your antennas up for interesting ideas that are starting to appear and being adaptable and willing to sort of explore and make use of new ideas, that's the way that you keep your thinking vibrant.
Cool. Yeah. And I think AI, machine learning, and NLP of all fields moves so fast. I think all of us just have to, keep learning. Right?
Absolutely.
Thanks, Chris. This has been great. And it's really interesting to hear the story of how you wound up doing all this work over these many years. And I find it inspiring to think that maybe there's someone watching this that will, follow in some of your footsteps and themselves maybe end up a professor somewhere or doing great research, much as you have. So thank you.
Thank you, Andrew. It's been fun chatting. A final fact I can tell people listening is, for a whole bunch of years, Andrew and me were actually office mates. We had the offices next door to each other on the corridor. And so once upon a time, I had opportunities often to see Andrew in the corridor and pass a few thoughts. I don't get those chances as often anymore, so it's fun getting a chance to chat.
Thanks, Chris. Those are good days. I remember we shared a wall, so if I hit my wall in my office, you're on the other side. So those great times. So thanks, Chris.
Okay, see you.
For more interviews with NLP thought leaders, check out the deeplearning.ai YouTube channel or enroll in the NLP specialization on Coursera.
This video will give you an overview of Bayes' rule and go over some probability. Don't worry if your math is a little bit rusty. We'll go through this together, step by step. Probability is fundamental to many applications in NLP, and you will see how you can use it to help classify whether a tweet is positive or negative. So let's get started. To start, we are going to first review what probabilities and conditional probabilities are, how they operate, and how they can be expressed mathematically. Then, I'll go over how to derive Bayes' rule from the definition of conditional probabilities. Bayes' rule is applied in many different fields, ranging from medicine to education, and is used extensively in NLP. Once you understand the theory behind Bayes' rule, you can use it to perform sentiment analysis on tweets, which will be this week's assignment. Then in the next course, you'll implement autocorrect using its basic formulation as well. Imagine you have an extensive corpus of tweets that can be categorized as either positive or negative sentiment, but not both. Within that corpus, the word happy is sometimes being labeled positive and sometimes negative. Let's explore why this situation is occurring. One way to think about probabilities is by counting how frequently events occur. Suppose you define event A as a tweet being labeled positive, then the probability of event A, shown as P of A here, is calculated as the ratio between the count of positive tweets in the corpus divided by the total number of tweets in the corpus. In this example, that number comes out to 13 over 20, or 0.65. You could also express that value as a percentage, 65% positive. It's worth noting that the complementary probability here, which is the probability of the tweet expressing a negative sentiment, is just equal to 1 minus the probability of a positive sentiment. Note that for this to be true, all tweets must be categorized as either positive or negative, but not both. Let's define event B
in a similar way by counting tweets containing the word happy. In this case, the total number of tweets containing the word happy, shown here as unhappy, is 4. Here's another way of looking at it. Take a look at the section of the diagram where tweets are labeled positive and also contain the word happy. In the context of this diagram, the probability that a tweet is labeled positive and also contains the word happy is just the ratio of the area of the intersection divided by the area of the entire corpus. In other words, if there were 20 tweets in the corpus, and 3 of them are labeled positive and also contain the word happy, then the associated probability is 3 divided by 20, or 0.15.
You now know how to calculate the probability of an intersection, for you know how to calculate the probability of a word, namely happy, with the probability of being positive. In the next video, we will talk about naive Bayes. Welcome! We will be looking at conditional probabilities to help us understand Bayes' rule. In other words, if I tell you you can guess what the weather is like given that we are in California and it is winter, then you'll have a much better guess than if I just asked you to guess what the weather is like.
In order to derive Bayes' rule, let's first take a look at the conditional probabilities. Now think about what happens if, instead of the entire corpus, you only consider tweets that contain the word happy. This is the same as saying, given that a tweet contains the word happy, with that, you would be considering only the tweets inside the blue circle, where many of the positive tweets are now excluded. In this case, the probability that a tweet is positive, given that it contains the word happy, simply becomes the number of tweets that are positive and also contain the word happy, and we divide that by the number that contain the word happy. As you can see by this calculation, your tweet has a 75% likelihood of being positive if it contains the word happy. You could make the same case for positive tweets. The purple area denotes the probability that a positive tweet contains the word happy. In this case, the probability is 3 over 13, which is 0.231. With all of this discussion of the probability of meeting certain conditions, we are talking about conditional probabilities. Conditional probabilities could be interpreted as the probability of an outcome B, knowing that event A already happened. Or, given that I'm looking at an element from set A, the probability that it also belongs to set B. Here's another way of looking at this with the Venn diagram you saw before. So, using the previous example, the probability of a tweet being positive, given that it has the word happy, is equal to the probability of the intersection between the tweets that are positive and the tweets that have the word happy, divided by the probability of a tweet given from the corpus having the word happy. Let's take a closer look at the equation from the previous slide. You could write a similar equation by simply swapping the position of the two conditions. Now, you have the conditional probability of a tweet containing the word happy, given that it is a positive tweet. Armed with both of these equations, you're now ready to derive Bayes' rule. To combine these equations, note that the intersection represents the same quantity, no matter which way it's written. Knowing that, you can remove it from the equation. With a little algebraic manipulation, you were able to arrive at this equation. This is now an expression of Bayes' rule in the context of the previous sentiment analysis problem. More generally, Bayes' rule states that the probability of x given y is equal to the probability of y given x times the ratio of the probability of x over the probability of y. And that's it. You just arrived at the basic formulation of Bayes' rule. Nicely done. So to wrap up, you just derived Bayes' rule from expressions of conditional probability. Throughout the rest of this course, you'll be using Bayes' rule for various applications in NLP. The main takeaway for now is that Bayes' rule is based on the mathematical formulation of conditional probabilities, and that, with Bayes' rule, you can calculate the probability of x given y if you already know the probability of y given x, and the ratio of the probabilities of x and y. So that's great work. I'll see you later.
Congratulations! You now have a good understanding of Bayes' rule. In the next video, you'll see how you can start applying Bayes' rule to a model known as naive Bayes. This will allow you to start building your sentiment analysis classifier using just probabilities. In this video, I will introduce you to log likelihoods. These are just logarithms of the probabilities we're calculating from the last video. But they are way more convenient to work with, and they appear throughout deep learning and NLP.
Okay, so let's go back to the table you saw previously that contains the conditional probabilities of each word for positive or negative sentiment. Words can have many shades of emotional meaning, but for the purpose of sentiment classification, they're simplified into three categories: neutral, positive, and negative. All can be identified by using their conditional probabilities. These categories can be numerically estimated just by dividing the corresponding conditional probabilities of this table. Now, let's see how this ratio looks for the words in your vocabulary. So the ratio for the word I is 0.2 divided by 0.2, or 1. The ratio for the word am is again 1. The ratio for the word happy is 0.14 divided by 0.1, or 1.4. Do the same for because, learning, and NLP. The ratio is 1. And for sad and not, the ratio is 0.1 divided by 0.15, or 0.6. Again, neutral words have a ratio near 1. Positive words have a ratio larger than 1. The larger the ratio, the more positive the word's going to be. On the other hand, negative words have a ratio smaller than 1. The smaller the value, the more negative the word. In this week's assignment, you'll implement a function that filters words depending on their positivity or negativity. You'll find the expression shown here to be very helpful with that. These ratios are essential in naive Bayes for binary classification. I'll illustrate why using an example you've seen before. Recall earlier, where you used the formula to categorize a tweet as positive if the product of the corresponding ratios of every word appears in the tweet is bigger than 1. And we said it was negative if it was less than 1. This is called the likelihood. If you were to take a ratio between the positive and negative tweets, you'd have what's called the prior ratio. I haven't mentioned it till now, because in this small example, you had exactly the same number of positive and negative tweets, making the ratio 1. In this week's assignment, you'll have a balanced data set, so you'll be working with a ratio of 1. In the future, though, when you're building your own application, remember that this term becomes important for unbalanced data sets. With the addition of the prior ratio, you now have the full naive Bayes formula for binary classification, a simple, fast, and powerful method that you can use to establish a baseline quickly. Now it's a good time to mention some other important considerations for your implementation of naive Bayes. Sentiment probability calculation requires multiplication of many numbers with values between 0 and 1. Carrying out such multiplications on a computer runs the risk of numerical underflow. When the number returned is so small, it can't be stored on your device. Luckily, there's a mathematical trick to solve this. It involves using a property of logarithms. Recall that the formula you're using to calculate a score for naive Bayes is the prior multiplied by the likelihood. The trick is to use a log of the score instead of the raw score. This allows you to write the previous expression as the sum of the log prior and the log likelihood, which is a sum of the logarithms of the conditional probability ratio of all unique words in your corpus. Let's use this method to classify the tweet. I'm happy because I'm learning. Remember how you used the naive Bayes inference condition earlier to get the sentiment score for your tweet. Now, you're going to do something very similar to get the log of your score. What you'll need to calculate the log of the score is called the lambda. This is the log of the ratio of the probability that your word is positive, and you divide that by the probability that the word is negative. Now let's calculate lambda for every word in our vocabulary. So for the word I, you get the logarithm of 0.05 divided by 0.05, or the logarithm of 1, which is equal to 0. Remember, the tweet will be labeled positive if the product is larger than 1. By this logic, I would be classified as neutral at 0. For am, you take the log of 0.04 over 0.04, which again is equal to 0. So you enter 0 in the table. For happy, you get a lambda of 2.2, which is greater than 0, indicating a positive sentiment. From here on out, you can calculate the log score of the entire corpus just by summing out the lambdas. You're almost done with the log likelihood. Let's stop here and take a quick look back at what you did so far. Words are often emotionally ambiguous, but you can simplify them into 3 categories, and then measure exactly where they fall within those categories for binary classification. You do so by dividing the conditional probabilities of the words in each category. This ratio can be expressed as a logarithm as well, called lambda, and you can use that to reduce the risk of numerical underflow.
In this video, you learned about the ratio of positive words to negative words. So the higher the ratio is, the more positive the word is going to be. As the number of words we are using gets larger and larger, then we are very likely to get a product that is very close to 0. Hence, we end up taking the log of that ratio. This part will be fun, as you will apply the naive Bayes classifier on real test examples. It is similar to what you did in the first video of the week, but we'll cover some special corner cases.
Once you have trained your model, the next step is to test it. And you do so by taking the conditional probabilities you just derived, and you use them to predict the sentiment of new, unseen tweets. After that, you'll evaluate your model performance, and you'll do so just like how you did it in the last week. You use your test set of annotated tweets. With the calculations you've done already, you have a table with the lambda score for each unique word in your vocabulary. And with your estimation of the log prior, you can predict sentiment on a new tweet. This new tweet says, I passed the NLP interview. You can use your model to predict if this is a positive or negative tweet. So before anything else, you must pre-process this text, removing the punctuation, stemming the words, and tokenizing to produce a vector of words like this one. Now, you look up each word from the vector in your log likelihood table. If the word is found, such as I, pass, the, and NLP, you sum over all the corresponding lambda terms. The values that don't show up in the table of lambdas, like interview, are considered neutral and don't contribute anything to the score. Your model can only give a score for words it's seen before. Now you add the log prior to account for the balance or imbalance of the classes in the dataset. So this score sums up to 0.48. Remember, if this score is bigger than 0, then this tweet has a positive sentiment. So yes, in your model and in real life, passing the NLP interview is a very positive thing. You just predicted the sentiment of a new tweet, and that's awesome. It's time to test the performance of your classifier on unseen data, just like you already did for a different scenario in the previous module. Let's quickly review that process. As applied to naive Bayes, this week's assignment includes a validation set. This data was set aside during training and is composed of a set of raw tweets, so xval, and their corresponding sentiments, yval. You'll have to implement the accuracy function to measure the performance of your trained model, represented by the lambda table and the log prior, using these data. First, compute the score of each entry in xval, like you just did previously. Then, evaluate whether each score is greater than 0. This produces a vector populated with zeros and ones, indicating if the predicted sentiment is negative or positive, respectively, for each tweet in the validation set. With your new predictions vector, you can compute the accuracy of your model over the validation set. To do this part, you will compare your predictions against the true value for each observation from your validation data, yval. If the values are equal and your prediction is correct, you'll get a value of 1. and 0 if incorrect. Once you have compared the values of every prediction with the true labels of your validation set, you can compute the accuracy as the sum of this vector divided by the number of examples in the validation set, just like you did for the logistic regression. Okay, let's revisit everything you just did. To test the performance of your naive Bayes model, you use a validation set to allow you to predict the sentiment score for an unseen tweet using your newly trained model. Then, you compared your predictions with the true labels provided in the validation set to get the percentage of tweets that were correctly predicted by your label. Then, you compared your predictions with the true labels provided in the validation set, and this allowed you to get the percentage of tweets that were correctly predicted by your model. You also saw that words that don't appear in the lambda table are treated as neutral words.
Now you know how to apply the naive Bayes method to test examples. In the coding exercise at the end of the week, you will use it to classify tweets. Next, I'll show you other things it can do. No matter what NLP method you use, you will one day find yourself faced with an error. For example, a misclassified sentence. In this video, I'll show you how to analyze such errors.
Let us consider some possible errors in the model prediction that can be caused by these issues. 1. Semantic meaning lost in the preprocessing step. 2. How word order affects the meaning of a sentence. And 3. Some quirks of language that come naturally to humans, but confuse naive Bayes models. So let's start. One of your main considerations when analyzing errors in NLP systems is what the processed version of the text actually looks like. Let's look at this tweet. My beloved grandmother, with some punctuation indicating a sad face. The sad face punctuation in this case is very important to the sentiment of the tweet because it tells you what's happening. But if you're removing punctuation, then the processed tweet will leave behind only beloved grandmother, which looks like a very positive tweet. My beloved grandmother, ! Would be a very different sentiment. So remember, always check what the actual text looks like. It's not just about punctuation either. Check out this tweet. This is not good because your attitude is not even close to being nice. If you remove neutral words like not and this, what you're left with is the following: good, attitude, close, nice. From this set of words, any classifier will infer that this is something very positive. I'll talk later on about handling not and word orders. But remember, double check what your processed text looks like to make sure your model will be able to get an accurate read. The input pipeline isn't the only potential source of trouble. Look at these tweets. I'm happy because I did not go. This is a purely positive tweet. I'm not happy because I did not go with a negative sentiment. In this case, the not is important to the sentiment, but gets missed by your naive Bayes classifier, so word order can be as important as spelling. There are many other factors to consider as well, and you will see more and more ways to build systems that handle them in the weeks to come. Another problem of naive Bayes is something called an adversarial attack. The term adversarial attack describes some common language phenomena like sarcasm, irony, and euphemism. Humans pick these up quickly, but machines are terrible at it. This tweet: this is a ridiculously powerful movie. The plot was gripping, and I cried right through until the ending, contains a somewhat positive movie review, but preprocessing might suggest otherwise. If you preprocess this tweet, you'd get a list of mostly negative words, but as you can see, they were actually used to describe a movie that the author enjoyed. If you use naive Bayes on this list of words, it would end up giving a very negative score regardless.
Now you know how to apply the naive Bayes method to text classification. It makes the independence assumption, which can lead to errors, but you know how to analyze them. It's still a very powerful baseline. As you know, it relies on word frequency counts. Next week, we can learn how to use word vectors that can give us better results. Last week, you learned about a classification algorithm known as naive Bayes. This week, you're going to learn about vector spaces, and specifically, you will learn what type of information these vectors could encode. You'll see different types of applications that you can use with these vector spaces, and you'll see different types of algorithms you'll be implementing. Let's take a look at an example. In this video, I'm going to introduce you to the general idea behind vector space models. You're going to see their advantages, along with some of their applications in natural language processing. So suppose you have two questions. The first one is, where are you heading? And the second one is, where are you from? These sentences have identical words, except for the last ones. However, they both have a different meaning. On the other hand, say you have two more questions, whose words are completely different, but both sentences mean the same thing. Vector space models will help you identify whether the first pair of questions or the second pair are similar in meaning even if they do not share the same words. They can be used to identify similarity for question answering, paraphrasing, and summarization. Vector space models will also allow you to capture dependencies between words. Consider this sentence. You eat cereal from a bowl. Here, you can see that the word cereal and the word bowl are related. Now, let's look at this other sentence. You buy something and someone else sells it. So what it's saying is that someone sells something because someone else buys it. The second half of the sentence is dependent on the first half. With vector space models, you will be able to capture this and many other types of relationships among different sets of words. Vector space models are used in information extraction to answer questions in the style of who, what, where, how, and etc. In machine translation and in chatbots programming. They're also used in many other applications. As a final thought, I'd like to share with you this quote from John Firth, a famous English linguist. You shall know a word by the company it keeps. This is one of the most fundamental concepts in NLP. When using vector space models, the way that representations are made is by identifying the context around each word in the text, and this captures the relative meaning. To recap, vector space models allow you to represent words and documents as vectors. This captures the relative meaning. You learned about vector space models, and you have seen different types of applications where these vector space models are used. In the next video, you will build them from scratch, and specifically, you will see how they are built using co-occurrence matrices. Hello! In this video, you're going to learn to manipulate vectors by performing some simple vector arithmetic, meaning by adding vectors or subtracting vectors, you'll be able to predict the countries of certain capitals. Let's dive in. I'll show you how to manipulate vector representations in order to infer unknown relations among words. Suppose that you have a vector space with countries and their capital cities. You know that the capital of the United States is Washington, D.C., and you don't know the capital of Russia, but you'd like to use the known relationship between Washington, D.C. and the USA to figure it out. For that, you'll just use some simple vector algebra. For this example, you are in a hypothetical two-dimensional vector space that has different representations for different countries and capital cities. First, you will have to find the relationship between the Washington, D.C. and USA vector representations. In other words, which vector connects them. To do that, get the difference between the two vectors. The values from that will tell you how many units on each dimension you should move in order to find a country's capital in that vector space. So to find the capital city of Russia, you'll have to sum its vector representation with the vector that you also got in the last step. At the end, you should deduce that the capital of Russia has a vector representation of 10, 4. However, there are no cities with that representation, so you'll have to take the one that is the most similar to it by comparing each vector with the Euclidean distances or cosine similarities. In this case, the vector representation that is closest to the point 10, 4 is the one for Moscow. Using this simple process, you could have predicted the capital of Russia if you knew the capital of the USA. The only catch here is that you need a vector space where the representations capture the relative meaning of words. Now you have a simple process to get unknown relationships between words by the use of known relationships between others.
You now know the importance of having vector spaces where the representations of words capture the relative meaning in natural language. In upcoming parts of this specialization, you will perform more sophisticated tasks taking advantage of this type of representation.
You have now seen a clustering of all vectors when plotted on two axes. You have also seen that the vectors of the words that occur in similar places in the sentence will be encoded in a similar way. You can take advantage of this type of consistency encoding to identify patterns. For example, if you have the word doctor, and you are to find the closest words that are closest to it by computing cosine similarity, you might get the word doctors, nurse, cardiologist, surgeon, etc. In the next video, you will learn how to plot these d-dimensional vectors on a 2D plane. You will now learn about eigenvalues and eigenvectors, and you will see how you can use them to reduce the dimension of your features.
First, I'll show you how to get uncorrelated features for your data, and then how to reduce the dimensions of your word representations while trying to keep as much information as possible from your original embedding. To perform dimensionality reduction using PCA, begin with your original vector space. Then, you get uncorrelated features for your data. And finally, you project your data to a number of desired features that retain the most information. You may recall from algebra that matrices have eigenvectors and eigenvalues. You do not need to remember how to get those right now, but you should keep in mind that in PCA, they are useful because the eigenvectors of the covariance matrix from your data, they give directions of uncorrelated features, and the eigenvalues are the variance of your datasets in each of those new features. So to perform PCA, you will need to get the eigenvectors and eigenvalues from the covariance matrix of your data. The first step is to get a set of uncorrelated features. For this step, you will mean normalize your data. Then, get the covariance matrix, and finally perform a singular value decomposition to get a set of three matrices. The first of those matrices contain the eigenvector stacked column-wise, and the second one has the eigenvalues on the diagonal. The singular vector decomposition is already implemented in many programming libraries, so you don't have to worry about how it works. The next step is to project your data to a new set of features. You will be using the eigenvectors and eigenvalues in this step. Let's denote the eigenvectors with U and the eigenvalues with S. First, you will perform the dot products between the matrix containing your word embeddings and the first n columns of the U matrix, where n equals the number of dimensions that you want to have at the end. For visualization, it's common practice to have two dimensions. Then, you'll get the percentage of variance retained in the new vector space. As an important side note, your eigenvectors and eigenvalues should be organized according to the eigenvalues in descending order. This condition will ensure that you retain as much information as possible from your original embedding. However, most libraries order those matrices for you. Wrapping up, eigenvectors from the covariance matrix of your normalized data give the directions of uncorrelated features. The eigenvalues associated with those eigenvectors tell you the variance of your data on those features. The dot products between your word embeddings and the matrix of eigenvectors will project your data onto a new vector space of the dimension that you choose. You are now ready to implement PCA in this week's assignment to visualize word representations. Good luck with that, and remember to have fun.
Congratulations! You now know all about PCA and you know all the steps required for you to implement it. Next week, you will learn about vector spaces, and I will show you how you can use them to build a simple machine translation system. In this video, you are going to learn about hash tables and hash functions. For example, imagine that you have a cupboard with several drawers. You might want to place similar objects in similar drawers. For example, paper documents alone, keys alone, and books alone. In this video, we will dive deeper into this concept.
So let us say you have several data items and you want to group them into buckets by some kind of similarity. One bucket can hold more than one item, and each item is always assigned to the same bucket. So the result would be these blue ovals end up in bucket number 1, these gray rectangles end up in bucket number 2, and these magenta triangles are assigned to bucket 3. Now let's think about how we'd like to do this with word vectors. First, let's assume that the word vectors have just one dimension instead of 300 dimensions. So each word is represented by a single number, such as 100, 14, 17, 10, and 97. You need to find a way to give each vector a hash value, which is a key that tells it which bucket it's assigned to. A function that assigns a hash value is called a hash function. In this example, here is a hash table, which is a set of buckets. In this case, the hash table has 10 buckets. Notice how the word vectors 110 are assigned to bucket 0. The word vector 14 is assigned to buckets 4, and the word vectors 17 and 97 are assigned to bucket 7. Do you notice a pattern? This formula here is the hash function that's being used to assign the word vectors to their respective buckets. The modulo operator takes the remainder after dividing by 10. The remainder is the hash value that tells us where the word vector should be stored. For example, 14 divided by 10 has a remainder of 4, so it goes to buckets 4. Now let's build a basic hash table in code. Here's a definition of a function that takes in a list of values. You can think of each value as a one-dimensional vector. It also takes in the number of buckets. Define the hash function used in the modulo operator. Then you create the hash table. Notice that this is a dictionary comprehension. The key is an integer, and the value is an empty list, which you'll use as a bucket for storage. For each word vector, calculate its hash value, then append it to the appropriate list. The hash table that is returned can be seen in the notebook that goes with this lecture. You'll see that the hash table is the same as what you saw in the previous slide. Now let's take another look at this basic hash table. Recall that your original goal was to put similar word vectors into the same bucket. But here, it doesn't look like numbers that are close to each other are in the same bucket. For instance, 10, 14, and 17 are in different buckets. Ideally, you want to have a hash function that puts similar word vectors in the same bucket, like this. To do this, you'll need to use what's called locality-sensitive hashing. Locality is another word for location. Sensitive is another word for caring. So locality-sensitive hashing is a hashing method that cares very deeply about assigning items based on where they're located in vector space. You'll learn about locality-sensitive hashing next.
So you learned a lot of new terms. You learned about hash values, hash functions, and buckets. You have also seen the code for how to build a hash table, or the equivalent of the cupboard I spoke about in the intro of the video. In the next video, we will look at locality-sensitive hashing. One key method that you will use to reduce the computational cost of finding k-nearest neighbors in high-dimensional spaces is locality-sensitive hashing. In this video, I will teach you what hashes are and where they are used.
To start thinking about locality-sensitive hashing, let's first assume that you're using word vectors with just 2 dimensions. I'll repeat each vector as a circle instead of arrows. So let's say you want to find a way to know that these blue dots are somehow close to each other, and that these gray dots are also related to each other. First, divide the space using these dashed lines, which I'll call planes. I'll explain why I call them planes in a bit. Notice how the blue plane slices up the space into vectors that are above it or below it. The blue vectors all happen to be on the same side of the blue plane. Similarly, the gray vectors happen to be above the gray plane. It looks like the planes can help us bucket the vectors into subsets based on their location. This is exactly what you want. A hashing function that is sensitive to the location of the items that it's assigning into buckets. You're working your way towards locality-sensitive hashing. Now let's see why I'm calling these dashed lines planes. A plane would be this magenta line into 2-dimensional space, and it actually represents all the possible vectors that would be sitting on that plane. In other words, they would be parallel to the plane, such as this blue vector, or this orange vector. You can define a plane with a single vector. This magenta vector is perpendicular to the plane, and it's called the normal vector to that plane. The normal vector is perpendicular to any vectors that lie on the plane. It might help to think about this in 3 dimensions. Find a sheet of paper and find a pencil. Place the paper on a table and draw some vectors on it. Then hold the pencil vertically over the paper. Any vectors on the paper are perpendicular to the pencil. Let's go back to 2 dimensions. You are able to see visually when a vector is on one side of the plane or the other. But how do you do this mathematically? Here are 3 sample vectors in blue, orange, and green. The normal vector to the plane is labeled P. Let's focus on vector 1. What if you take the dot product of P with vector 1? You get 3. I'll explain in a bit why you're doing this. Now let's look at vector 2. If you take the dot product of P with vector 2, you get 0. Finally, let's look at vector 3. If you take the dot product of P with vector 3, you get negative 3. So the dot products are 3, 0, and negative 3. Do you notice something about the signs and how they're related to their position relative to the red plane? When the dot product is positive, the vector is on one side of the plane. If the dot product is negative, the vector is on the opposite side of the plane. If the dot product is 0, the vector is on the plane. So what's the dot product doing? To visualize the dot product, imagine one of the vectors such as P as if it's the surface of the Earth. Gravity pulls all objects straight down towards the surface of the Earth. Next, pretend you're standing at the end of the vector, V1. You tie a string to a rock and let gravity pull the rock to the surface of vector P. The string is perpendicular to vector P. Now if you draw a vector that's in the same direction of P, but ends up at the rock, you have what's called the projection of vector V1 onto vector P. The magnitude or length of that vector is equal to the dot product of V1 and P. Furthermore, if you had this other green vector and projected it onto vector P, the projected vector would be pointing in the parallel but opposite direction of P. The dot product would be a negative number. This means that the sign of the dot product indicates the direction of the projection with respect to the purple normal vector. So, whether the dot product is positive or negative can tell you whether the vector v1 or v2 are on one side of the plane or the other. Let's use code to check which side of the plane a vector is on. The function side of plane takes in the normal vector p and a vector v. Use numpy dot to take the dot product. Use numpy dot sign to get a +1 if the dot product is positive, -1 if the dot product is negative, or 0 if the dot product is 0. I'm using numpy dot as scalar. Notice the pronunciation of that function. If a vector can be represented as a single scalar, this function retrieves that scalar. And that's it. Please try it out for yourself.
That was a lot of visualizations and a lot of projections. The main takeaway is that the sign of the projection of two vectors tells you which parts of the line the point lies. For example, above it or below it. In the next video, you will learn how to combine this concept with multiple planes to try to better approximate where a data point might be located.